All right, so just an introduction to this idea of mathematical induction. And I want to start with an example of a partial sum. So we're just going to look at something we've already done. I want to look at, so let's look at the partial sum. Now, if you remember, partial sums, we talked about earlier, we labeled those as S sub n. So whatever the number of the terms are that you're adding together, that's what n would be. So we're going to look at the partial sum for positive odd integers. And we're just going to look at the first few terms. Okay, so we're going to start with S sub 1 and go up to maybe S sub 5. And I want to see if we can find a pattern. So looking at this from just the standpoint that we've done these before, so S sub 1, what that means is we're going to take one odd integer and add it, just that one odd integer. We don't actually have to add anything because it's just one thing. The sum is just 1. Now, what I'm going to be concerned with here are the sums. So I'm just going to highlight the sums as we go through this process. Okay, so the first term, first partial sum is 1. So the second partial sum means now do 2 terms in that sequence. So 2 terms that are positive odd integers. So starting with 1, then we add 3. So 1 plus 3. And that is 4. So the sum is what I'm concerned with here. All right, the work that we do to get to the sum is somewhat important, but for right now, I'm focusing on what we get when we add these together. So then S sub 3, that means we add the 3 first odd integers together. So that'll be 1 plus 3 plus 5. 1 plus 3 plus 5, that's 9. So now I'm looking at the sum. All right, let's keep going. Go ahead.
Where did you get the 3 and the 5 from?
So I'm adding the first 3 odd integers. So that's 1 is 3. Yep. So I'm just continuing to add on to my previous sequence. That's all I'm doing. So S sub 4, again, the first 4 odd integers is what I'm adding together. So 1 plus 3 plus 5 plus 7. So 1 plus 3 plus 5 plus 7. So that's 8 plus 8 is 16. So that's my sum. All right, let's do one more. So S sub 5, add the first 5 odd integers together. So that would be 1 plus 3 plus 5 plus 7 plus 9. So 10 plus 10 plus 5 would be 25. Okay, so I'm going to stop there. And I want to just take a look at those first 5 terms in that sum. Okay, so we're finding the partial sums. I'm saying if n is 1, this is my sum. If n is 2, 4 is my sum. If n is 3, 9 is my sum. Okay? I'm giving you a way to think about, okay, so the sum of those positive odd integers looks like it's going to be 1 plus 3 plus 5 plus 7, all the way up to whatever we get when we plug in n is going to be what? How could I figure out the sum for any of our odd integers? Do you see a pattern? So if n is 1, our sum is 1. If n is 2, our sum is 4. If n is 3, our sum is 9.
So you're basically multiplying it by itself.
Perfect. Yes. So in mathematical terms, we're squaring it. So I could say take whatever n is and square it. Now, we could very easily test this out for any n value, right? I could say, okay, well, what if n is 100? Now, it would be a lot of numbers to add together, but it wouldn't be difficult to prove. what we're going to do is we're actually going to go into how we would prove this tomorrow for sure. We're going to set it up today. This is the introduction to this idea of what it is that we're going to be proving. We're going to be proving that the sum of some number of numbers in whatever the pattern is a formula. And we're going to show what that formula is and then prove that it's true. But for today, we're going to talk a little bit about just what that all means. So this is we're going to come back to visit this again. We can kind of see that this is true, but it's really dangerous in mathematics to just jump to a conclusion and assume that it's going to be true always. And I'm going to show you why that is here in just a second. So we have this guy named Pierre de Fermat, and he was a French, I assume, by the name. Pierre de Fermat, sounds French to me. A French mathematician in the 1600s. And he thought he had come up with a way to generate prime numbers. Now, you might be thinking to yourself, big deal, who cares? But the idea of a prime number in mathematics is a really important idea. And the problem of generating prime numbers with an equation is still an unsolved problem today. Like, we haven't been able to come up with a formula that will generate just prime numbers. Now, before we go any further, do you understand what a prime number is? We need to start there. What's the definition of a prime number, if you had to explain it to someone? What do you think?
A number that's only divisible by 1 in itself.
Perfect. So a number that's only divisible by 1 in itself. Okay? So prime numbers can only be able to be divided by 1 and itself. So like 5. 5 is a prime number because you can only divide it by 1 and 5. 4 is not a prime number because it can be divided by 1, 2, or 4. Okay, so here we go. So here he is, Fermat. He's thinking, hey, I've got this formula. It's going to generate, I keep wanting to say odd numbers. It's going to generate prime numbers. And he had a hard time showing that that was true. Now, keep in mind, he did this in the 1600s. Okay, so imagine that we don't have the technology that we have today to do the computations that we're about to do. Okay, so Fermat, we'll just write a little description of what this is. So Fermat thought he had a formula that would only generate prime numbers. Now, there's a really important distinction that we need to remember here. What he is not saying this formula would do would be to generate every prime number. Okay, he's not saying that he's going to generate every possible prime number. He's saying that if you plug in a number into this formula, the outcome will be prime. That's what he's saying. So here's what Fermat thought his formula was. So we'll call it F for Fermat. F sub n is 2, get ready for this, to the 2 to the n power plus 1 for n equal to 0, 1, 2, and so on. So our n values have to be integer values, including 0. So greater than or equal to 0, integer values only. So let's try computing a few of these. So here's how Fermat started to kind of attack this. He wanted to show that it was true. So he wanted to generate the first few terms and show that the first few terms were in fact prime. So f sub 0, let's start there. That means we're going to plug in 0 for n. Now I'm going to take this pretty slowly here just because I don't want us to make any mistakes. And I want us to truly understand how you would compute this. So I'm going to start out plugging 0 in for n and then figuring out what 2 to the 0 power is. So 2 to the 0 power is just 1. So we're really saying do 2 to the first power plus 1. Well, that's 2 plus 1, which is 3. Now, would you agree that that is a prime number? Very easy to verify that, right? 1 is only divisible by 1 in itself. Okay, so we've got that this is a prime number. Awesome. Let's do the next one. So 2 to the 2 to the first power. So again, I'm going to be very systematic here. I'm going to do 2 to the first power, which is 2. So now I've got 2 squared plus 1. Not bad. 2 squared, that's 4. 4 plus 1 is 5. I think we all can agree that 5 also a prime number. So first couple terms, not too bad. Let's keep going. We're going to do maybe the first 5 terms. So let's do f sub 2. So that's 2 to the 2 to the second power plus 1. So I want to figure out what 2 squared is. Well, that's 4. So I'm really doing 2 to the 4th power. 2 to the 4th power, 16, plus 1 is 17. 17, is it prime?
Yes.
Yeah, that one's pretty easy to figure out, right? We know just probably from our experience that 17 is going to be prime. Again, it's important to note the distinction in what we're proving or what we're showing. He's not writing a formula that will generate all prime numbers because clearly there's a big gap between 5 and 17 where there are some prime numbers that we didn't get. This is just saying that when you generate a number from this formula, you should get a prime number. Okay, what about f sub 3? 2 to the 2 to the 3rd power. So I start with this, 2 to the 3rd power. That's 8. So 2 to the 8th power. Now we're getting into powers of 2 that maybe we don't know offhand. Maybe you do. It's essentially going to be 16 squared, which is 256. Which is 257. Now, do you know just by looking at 257 that this is an odd number? Or a prime number, sorry. No, definitely not. We couldn't look at that and say, oh yeah, obviously that's odd. We'd have to do a little bit of work there, right? We'd have to decide, is there anything that could divide into 257 nice? But let's just give Fermat the benefit of the doubt. Like that's not difficult to do. It would just take a few minutes for him to go through and show that you can't divide 257 by anything except for itself and 1. So let's give him the benefit of the doubt. And let's say, yeah, okay, Fermat, you got it. 257, it's prime. Nice work. Let's move on. Let's do, I'm going to zoom out just a little bit here. F sub 4. So now we've got 2 to the 2 to the 4th power plus 1. 2 to the 4th power. I don't know about you. I don't know what that is offhand. No, 2 to the 4th power is, sorry, that's 16. So we're doing 2 to the 16th power plus 1. It's 16 that I don't know what that is offhand. So it's 65536. I just did this a little bit earlier using calculator plus 1. So here I get 65,537. I don't know. Do you know if that's a prime number? Again, I don't know either. I mean, it wouldn't be difficult to show that it's prime. It, again, would just take a little bit of time. But remember, Fermat's dealing with not having a calculator. This is the 1600s we're talking about. So he's like, all right, yeah, sure. This is prime. I can show it's prime. I'm going through the work. I showed that you can't divide it by anything except itself in 1. Okay, so he did the work for that. But then this happens. F sub 5. So just like before, I'm taking it slow. I'm figuring out what 2 to the 5th is, and that's the power of 2 I'm going to have to find. Now I have to do 2 to the 32nd power. Okay, no calculator. Try to figure out what 2 to the 32nd power is. I mean, that's going to take a while, right? So using our technology, we can come up with this. Now, if you do it on Desmos or on your calculator, you're going to get an answer in scientific notation. So we get 4.29 blah, 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 blah times 10 to the 9th power. And that just means let's take the decimal point and move it over 9 places. So I think our number is just going to be exactly what we're seeing on screen here. And for those of you at home, maybe can't see this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm going to go ahead and write it out. Because I want to just explore the idea that this number is large. So I'm writing this out, whoops, where'd it go? Without the decimal. So we have 4, 2, 9, 4, 9, 6, 7, 2, 9, 6, plus 1. So that, what is that? That's a really large number. 4 billion, over 4 billion. Okay, and then we add 1 to that. That's easy, right? That part's not difficult. So add 1, and we get 4,294,967,297. Do you see the issue here? Fermat wants to show that this is an odd number. I'm sorry, a prime number. Even with calculators, trying to show that a number over 4 billion is prime is going to be a huge undertaking. So you get to this point, like he just says, here's my formula, it works. And then somebody starts generating terms and they're like, really, Fermat, this works? I don't know. I don't trust you here. So this became sort of something that became a problem in mathematics. And then, I don't know, over 100 years later maybe, sometime in the 1700s, I don't know the exact date, this mathematician named Euler, who's responsible for a lot of what you see in geometry even, and I'll put his name up here in just a second, actually showed that this is not prime. He was able to actually show it's not prime. So let's just put that little side note in here. So we get to this point where like, yeah, I don't know. I can't actually believe you that that's a prime number. You're going to have to give me a little bit more. So in the 1700s, I don't know exactly when. I don't think it's that important. This mathematician named Euler, and yes, it's spelled E-U-L-E-R, but it's pronounced Euler, showed that f sub 5, that thing that we wrote before, was actually equal to 600 times 6,700,417, meaning it's not prime. Now, it took 100 years, right? Because we're talking about Fermat was in the 1600s, Euler was in the 1700s. It took that long for someone to actually show that, hey, this actually isn't a prime number. So Fermat, his conjecture for his equation, ended up not being a true statement. But it took a long time for them to actually prove it. So the lesson here is this. If we go back up here, we're looking at our partial sum, 1, 3, 5, 7, blah, 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 blah. We're saying it equals n squared, but we only looked at 5 terms. While our formula, our sequence, our sum for this one is a lot easier to look at and work through, it's still not enough. We are making a conjecture by saying this thing is going to always be n squared. But we've got to show that that's actually true. And we'll do that because, like, look at the lesson we learned from Fermat. Even with 5 terms, which is not very many terms, he got stuck. So we've got to come up with a better way. And that better way is mathematical induction. So here's how mathematical induction is going to work. So we're going to use this idea of mathematical induction as a way to prove a conjecture is true. So no longer are we just going to say, well, it looks like it. Good enough for me. We're going to actually use this type of proof that's pretty common with this idea of sequences and partial sums. So what does that look like? So mathematical induction is going to start like this. You're going to get, we're just going to number this kind of in the order that you'll see things. Let P sub n, I know this is going to seem like some very weird kind of talk here in a moment. Just stick with me and it'll get a little bit better as we work through it. Let P sub n be a statement using the positive integer n. I wrote a very important thing there. I don't know why I'm lagging here for a moment. There it is. I wrote a very important thing there, that idea of a positive integer. This is really important. That means that n can't be something like 3.7 or -5. It has to be a positive integer. So something like 1, 2, 3, 4, 5, 6, 7, and so on. So here's what we're going to do. We're going to start. So that's kind of what we're going to be given. We're going to be given this idea that there's some statement involving n. The first thing that we're going to do is we're going to show that P sub 1 is a true statement. We are literally just going to plug in 1 and show that it actually gives us the proper sum. So going back to what we did as our first kind of example here, if I'm stating that n squared is the way that we can find the sum of all positive odd integers, then what I'm going to do is say, okay, let me plug in 1 for n. If I plug in 1 for n, I get 1 squared, which is 1. And if I show what the sequence is, it's just going to be 1. So I'm able to prove it by looking at, or I'm starting my proof by just looking at, does the first number in the sequence actually work? That's our first step. So the first thing we'll do is we'll show, does it work for the first number in our sequence? So is P sub 1 true? Okay, and then we're going to do two things here. We're going to write a P sub k and P sub k plus 1 statement. Now you might be asking yourself, what? Where's k coming from? With sequences, we do use k a lot. K, I, j. Those are just kind of common letters in addition to n that are used with sequences. This is just the setup for our proof. Okay, so I'm going to write these statements. I'm going to write P sub k and P sub k plus 1. And then we're going to actually write the proof. So this is actually the actual proof part. The first couple steps are just the setup. What we're going to show is if we can show for every positive integer k, this is again going to seem some really intense math speak, but just go ahead and follow along with me for a minute. The truth of P sub k implies the truth of P sub k plus 1 then the statement P sub n must be true for all positive integers n. Okay, that's math speak. Let me try to explain this in a less intense way. Essentially what we're saying is, if we can show that it works for the first term, so P sub 1, then we're essentially doing a recursive type proof. If you remember what recursive means, it means you find any term in the sequence by doing something to the previous term. So we're going to show that recursively this will work for any next term in the sequence. In other words, I can show that if it works for P sub 1, it's going to work for P sub 2. If it works for the first term, it works for the second term. Then if it works for the second term, it works for the third term. And I keep doing that, and I eventually say, well, if it works for some integer k, then it's going to work for the next term, which essentially says that I can pick k to be anything, then it will work for that next term in the sequence. And that's our goal. Okay, so what I want to do today is what you'll be doing. We're going to sort of set up our proof idea today, but we're also going to talk about what you'll have to do for your assignment tonight. All right, so let me try to write this in a way that makes sense. So example 1 here. All right, so given S sub n equals 1 plus 5 plus 9. I'll explain what we're writing here in just a second. 4 times n minus 1 minus 3 plus, I need to give myself a little bit of room here, 4 times n minus 3. So let's say that this is just how we generate the terms of our sequence, okay, S sub n. We generate the terms by saying 1 plus 5 plus 9 plus ... Any term in the sequence can be found by just doing 4 times the term number minus 3. So if I wanted to find, term 20, I would plug in 20 for n. And if I'm doing the sequence, then the term before that would use 19 for n, which is why this says n minus 1, right? If this is 20, this is n minus 1, which is 19. And then we keep working backwards till we get down to 1. All right, so this is how the partial sum would be written. Okay, let's say that I know, or I'm conjecturing, that we can find that sum by doing this. N squared times n plus 1 squared over 4. Okay, this is my conjecture. To find any partial sum for this sequence, I can use n squared times n plus 1 squared over 4. So if I plug in 4, I get 4 squared times 5 squared over 4, that would give me my sum. All right, so I'm kind of walking you through the first couple steps in this process, and then I'll just explain what it is that you're going to be responsible for tonight. So we're doing the setup today, and we'll actually go through the proof tomorrow. So in the process, I said you're going to be given this statement P sub n using some positive integer n. We're not going to do show P sub 1 is true today because we'll do that tomorrow. But I want to write the P sub k and P sub k plus 1 statements. Okay, so let's do that piece of it. That's all I want to do right now. So let's write P sub k, and then we'll do P sub k plus 1. So let's start with P sub k. I guess I should also say, where's P coming from? P, we could think of as this. The P sub n is that entire equation that we have written there. It's just another way to write it. So when I'm saying write P sub k plus, or P sub k, I'm asking you to write the original sequence. Let me zoom in a little bit here while we do this, and we'll just kind of move through this. 1 plus 5 plus 9 plus ... all the way up to, and I'm just going to replace n with k. So I'm not really doing anything other than just replacing n with k. And I need to do that over here as well. So I would have k squared times k plus 1 squared over 4. I apologize, it's a little tough to see right there. Okay, that's the P sub k statement. This will be given to you tonight. So you're going to be given this statement right here as your P sub k statement. All right, so that's what you're going to start out with tonight. Your job is to then write the P sub k plus 1 statement. So that's what we're going to do next here together. So this is part of, or this is only of what you'll be doing tonight. So write the P sub k plus 1 statement. Okay, so let's think about what that is telling us to do. So when I say write the P sub k plus 1 statement, I'm saying take every single k value in that expression and replace it with k plus 1. So everywhere I see k, let me go over and show you the rest of the formula here. Anywhere I see k, I'm going to replace it with k plus 1. That's my goal. So let's do that. All right. I'll keep that on the screen so we can see it. All right, so we've 1 plus 5 plus 9 plus ... plus. All right. So instead of k, I'm going to use k plus 1. So it'll be 4 times, it'll be k plus 1, and then minus 1, minus 3. So that's that first term that we see there with k in it. Okay, and then I'm going to write it for the next term as well. So plus, instead of k, I'm going to write k plus 1 minus 3. Now I need to do that other piece of the equation as well. So instead of k, I'm going to write k plus 1. So I will have k plus 1 squared replacing k with k plus 1 times, instead of k, k plus 1 plus 1 squared over 4. Okay, so I just want to do a tiny bit of cleanup here. Nothing totally like crazy, because that's what the proof will actually do. Let's just clean this up a little bit. So I have p sub k plus 1 equals 1 plus 5 plus 9 plus ... plus. Okay, so instead of being k plus 1 minus 1, I could just write that as k. Plus, instead of being 4k plus 1 minus 3, I don't care if you leave it like that. We're probably at least going to want to distribute and simplify a little bit. So we're going to have 4k, then we'll have 4 minus 3, which is plus 1. If you're not totally showing or following how I simplified that, distribute the 4 and add like terms. That's all we're doing there. Now on the right side, let's simplify this just a little bit. The k plus 1 squared, I'm not going to actually multiply anything out here. I'm just going to simplify what's in the parentheses. So k plus 1 squared just is fine. But then we have k plus 1, which is k plus 2 squared over 4. Okay, so let me just give you an idea of where this is going. We're going to stop with this process right now. We skipped the showing the P sub 1 statement is true. We'll do that tomorrow in the setup of our proof. But for now, we need to be able to come up with the k plus 1 statement. So tonight on your homework, I'm going to give you what's highlighted up there, and you have to come up with this and just this. Okay, so for your homework tonight, they're going to give you the P sub k statement. You come up with the P sub k plus 1, but just the formula part of it, not the actual like series. Okay, I want to do one more, and I want to set this one up a little bit more diligently, because we're going to finish the actual proof for it tomorrow. So we're going to go through the beginning setup of it again tonight, knowing you just have to do this part that I highlighted. All right, so let me see here. We'll start with what this looks like. So we'll revisit what we started with at the beginning of class. Okay, so we're going to revisit that original sum, partial sum. So let's say we have S sub n is 1 plus 3 plus 5 plus 7 plus... So that's that series we were talking about at the beginning of class, right? It's the sum of the positive odd integers. What we didn't talk about was, well, how do you generate each term in that series? And I'm not concerned, we aren't going to have to figure that part out. It's going to look like this. 2 times n minus 1 minus 1. And I probably should have used brackets there, but that's okay. Plus 2 times n minus 1. So what this is saying is to generate any term in the sequence, we do 2 times n minus 1. So if we wanted to generate the sum of the first 200 terms, to get all the terms, we would do 2 times 200 minus 1, then 2 times 199 minus 1, then 2 times 198 minus 1, and so on. And we would add all those together. But our conjecture is this. We said we think that this is just going to be n squared. Okay, that's what we came up with. So this is our S sub n statement. This has something to do with n. All right, I am going to go ahead. I'm not going to ask you to do this tonight, but I am going to go ahead and show that this is true when n equals 1. Okay, so like I said, we're just setting up this proof for tomorrow. So show n equals 1 is true. And we've actually done this, but let's just show it. So here's how we would show it. We say, okay, S sub n, well, S sub 1, the first term of the sequence is just 1, and that's it. That's our sum. But then we have to show that that is equal to 1 squared as well, which is also equal to 1. Okay, I showed that the first term in the sequence being 1 is equal to what I get when I plug 1 into my possible formula. Okay, so that's showing that n equals 1 is true. The second part of this is writing the S sub k statement. So we're going to write the S sub P sub k, sorry. So that means we go up to our sequence and we say, okay, that is just 1 plus 3 plus 5 plus 7 plus ... plus. And then I replace all of my n's with k's. That's it. Replace all of our n's with k's. So 2 times k minus 1 plus 2 times k minus 1 equals k squared. Okay, now I'm going to write my P sub k plus 1 step. Now this is the step that you'll have to write tonight. Okay, so let's just keep that all in mind as we're going through this process. The rest of this is what we'll talk more about tomorrow, but we're just kind of setting it up for tomorrow. Write the P sub k plus 1. So replace all of the k's with k plus 1. Okay, so we've got 1 plus 3 plus 5 plus 7 plus ... plus. Instead of 2 times k minus 1 minus 1, I'm going to write that as 2 times, replace k with k plus 1, minus 1, minus 1. Looks complicated, but remember we're just replacing k with k plus 1. Plus 2 times k plus 1 minus 1. Again, replacing k with k plus 1. And we believe that that should be k plus 1 squared. Now we'll finish kind of cleaning things up tomorrow. I don't want to do anything as far as housekeeping on this, except just to look at the end of this, because this is what you're doing for homework tonight. You're going to be given this, and you have to write this. Okay, so given this, write this. The The rest of this is just preparing us to finish this proof. I didn't want to do just part of it when we're going to actually finish the proof tomorrow. So we're going to stop with that proof right there. We're going to finish with our notes tomorrow. Are there questions on this before I take a look at the homework with you? Okay.